Now that you know how to build circuits on your breadboard, let's talk about different ways to configure circuits on your breadboard. So you have multiple resistors, and sometimes you might configure them in different ways on your breadboard. So you might have what we call series circuits or parallel circuits or a combination of both. So if you have series resistors, basically you have one resistor right after the other. And you might think about that in terms of a book series or a movie series or a TV show series. So series 1, series 2. And so you would want to watch one right after the other. They kind of add to each other chronologically. And so a series circuit is a lot like that. The electrons flow through one resistor, then the other, then the next one. And so you would want to look at them that way. Parallel circuits, on the other hand, basically the electrons will divide and pass through each resistor and then combine back together before they go to ground. And so you kind of can look at them as separate circuits. My analogy for that would be like an anthology series. So if you've seen shows on TV where season 1 doesn't really relate to season 2, you can watch season 4 before you watch season 2, and it's not going to change the story because they change the storyline each time. That's what we call an anthology series. And so I relate that to parallel circuits. You can kind of look at each individual loop of the circuit separately. And then sometimes you might have a combination of all of them, combination of series and parallel. And then in order to analyze these circuits, whether they're just series, just parallel, or the combination, we need to look at those resistors and see how they behave as one singular resistor. So what we'll do is we'll find what we call an equivalent resistance. So we'll look at all of the resistors, whether there's 2 or 42, and combine them into one singular resistor. And that will help us analyze and apply Ohm's law to the circuit. First, let's go ahead and build a series resistor circuit. So the series resistor circuit we're going to build will involve a 220 ohm resistor. So get your 220 ohm resistor, remember your color code. Take a second, look at the color code and think about what resistor value, what resistor you need to get. You'll also need a 1000 ohm resistor. Again, look at the color code and make sure you get the proper resistor. And you will also need a 470 ohm resistor. Okay, once you have your resistors, let's go ahead and build them on the breadboard. Now, we are not going to use the power supply. We're not going to power these resistors. We want to measure the resistance, and you can't measure the resistance using your multimeter when they're connected to a power source. So we're going to start with and look at the resistor circuit that I have, the diagram that I have showing on the screen, and we want to build that. And so in order to build that resistor, we need to have the start of the resistor, and you're going to plug it into some row. So you're going to start the resistor and plug it into some row, any row, it doesn't matter, and then you're going to plug the other end of the resistor into some other row. Don't plug it into the same row. If you plug it into the same row, imagine if we did have it connected to power. Then this whole row is connected. Current will just go straight through that row, and it won't ever go through that resistor. So you never want to have a component of your circuit where you have one end plugged into the same end, one end and the other end plugged into the same row of the resistor. We call these individual rows nodes, and so you don't want the resistor plugged into the same node from one end to the other. So always plug it into a separate row. Now, if you're looking at the schematic of the resistor circuit, you see that the second resistor should be plugged in, should be connected to the first resistor. So notice how I connected to the same row, but then the other end of this resistor needs to be connected to some other row. So that's helping us build our circuit. So we have it plugged into some other row. So notice what happens here. Imagine if this was connected to power and you were current moving through here, you'd go through this resistor, and because this resistor and this resistor are connected through that node or this row, row 10, it would go through this resistor and then go to this row here, row 16. And then finally, we're going to put our last resistor. This is the 1000 ohms. So we have our 220, our 470, and then our 1000 ohm resistor. I'm going to plug it into this row. That's the same end of where this 470 ohm resistor is connected to, so they're in the same node. And then it's going to be plugged into some random row on the breadboard. And so now imagine if this was connected to power. Again, we're not going to connect it to power, but imagine if it was, current could pass through this resistor, and because these two resistors are connected on this row here, or this node, the current can continue to pass through this resistor, and then it'll pass through this resistor here and close out to ground if that were connected to ground. Now get out your multimeter, and we're going to turn our multimeter to measure resistance. So turn it to measure resistance, set it to the ohm measurement, and write down what these resistance values are. So this first resistance value here, when I measure across it, now it doesn't matter which way you have it measured, which way you have it configured, it should give you the resistance value. So I have 217. So take a second and write down what your value is. 217 ohms. Now notice, remember, it's 0.217 kilo ohms, but if I convert that to just ohms, it should be 217 ohms. Now I'm going to measure just across this resistor, and it should be close to 470 ohms, and I get 462 ohms. And then I'm going to measure across my 1000 ohm resistor and see what I get. Now because I'm measuring across these individual resistors, I'm getting their individual resistance values. So I get 0.993 kilo ohms, which is 993 ohms. Now, notice how these resistors are all connected. From this point right here, this resistor is basically like a loop. So we have this resistor that's connected to this resistor, connected to this resistor. So I'm going to take my multimeter and I'm going to measure starting at this part of this resistor. So starting at the beginning of the resistor, series resistor circuit, and then I'm going to measure at the end of the series resistor circuit. And so what that's doing is it's combining this resistor, and this resistor together, and it's giving me the equivalent resistance that these three resistors provide. Looking at my multimeter, I get 1.672 kilo ohms, which is 1,672 ohms. Now look at that number and write yours down. Look at your numbers because yours are going to be different. Remember, your manufacturer tolerances, you're going to have different values for your resistances. And decide, can you figure out a relationship between these three individual resistors and the overall equivalent resistance that these three resistors provide? Looking at the math, you should see that adding the three individual resistors together, when I add 217 plus 462 plus 993 ohms together, I get 1,672 ohms, which is what I measured when I put my multimeter across all three of these resistor values. So you can conclude that when the resistors are in series, the way you find the equivalent resistance is you just add them together. So it's very simple. When they're in series, you add one right after the other and add them together. Now, let's switch to parallel circuits. So looking at the parallel circuit that's shown on the screen, let's rebuild this circuit as parallel. Now notice how the parallel circuit, you have all of the resistors are connected at the top and all of the resistors are connected at the bottom. So the end, like one side of the resistor, one side of this resistor should be connected to one side of this resistor. So if you were looking at these two resistors, these should be connected here, and then the bottom should be connected here. So how do you put them on the breadboard such that they're connected? You put them in the same rows. So I take my 220 ohm resistor and I put one end right here on this row, and I put the other end on some other random row. Then in order to make these parallel with one another, I need to have one side of the 470 ohm resistor also in the same row as the 220, and the other side on the same row as the other part of the 220 resistor. And same thing with the 1000 ohm. So notice how I'm putting them all in right here, all the tops. Look how this matches the circuit diagram where you have the top row here. All of these, imagine if this was connected to positive and negative, all of these are connected, and then all of these are connected down here. So that's parallel. So I built these resistors to be in parallel with one another. Let's see if I measure across each individual one. Write down the values that you get. Y'all do this with me. So I'm measuring across the 220 ohm, and I get 129.1 ohms. Okay, well that's not 220, so I'm a little confused by that, but let's keep going. Just power through it. Let's measure across the 470 ohm resistor. Again, I get 129.1 ohms. Now let's measure across the 1000 ohm resistor. I'm getting 129.1 ohms. Why do you think I can't get the individual resistance values when I measure across the resistance? It's because they're all completely connected at these nodes, this node up here and this node here. So no matter where I measure this resistor, I'm getting the equivalent resistance value. So the equivalent resistance value of this parallel circuit is 129.1 ohms. Now, that's not as intuitive to see, oh, like series, you can just add them together and get that value. Instead, it's a little bit more complicated, and that it's actually a smaller value than any one of these individual resistors. So this 220 ohm resistor and this 470 ohm and this 1000 ohm, all three of these are greater than the overall equivalent resistance value. So somehow, when you put them in parallel, it actually reduces the size of the resistor when you find its equivalent resistance. Let's look at the math on how that happens. Okay, so when we're measuring the equivalent resistance across the three resistors in parallel, we notice that the resistance value became smaller than the smallest resistor in the parallel circuit. And so we know somehow it's reducing in size, and so it's a portion of what the individual resistors are. And so the equivalent resistance for resistors in parallel is a fractional version of the resistance values. And so what it is 1 over the summation of 1 over each individual resistance value. So you can see it's 1 over 220 ohms plus 1 over 470 ohms plus 1 over 1000 ohms. And so that gave us, for our physical measuring, 129.1 ohms. If we use the full 220, 470, and 1000, you would have gotten 130.3 ohms. Generalizing that into an equation, you can see here the equivalent resistance is 1 over the summation of 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3 for however many resistor values that you have. Let's work a problem to understand how to combine these parallel resistors a little bit better and why you might need to combine them to find the equivalent resistance. This resistor circuit here has two resistors that are in parallel with one another. One is 2 ohms and one is 6 ohms, and it has a 3-volt power supply or power source. And we want to find the total current supplied by the resistors. So we know Ohm's law. We already know Ohm's law is V equals I times R. Now we're trying to find current, so we can use Ohm's law to find current, but the question is, well, this has two resistor values. Which resistor do we use in Ohm's law to find the current that's supplied by the resistor? By the power source. Notice the current leaving the power source would be like this right here. Well, you can't use any one individual resistor. You have to combine them together into one equivalent resistance. So we have to find that REQ. So in order to find the REQ, you need to identify, are these in series or are these in parallel? Well, these two are in parallel. You can tell that by the fact that it forms a different loop to get from positive to negative. So if you go from positive and you go through this resistor, you can have one loop to get to negative. If you go from positive and you go through this resistor, you have a separate loop. That's important. We'll talk about that later on when we talk about how current goes through circuits. So we see that there's two resistors in parallel, and we remember that the equation to find resistors in parallel is 1 over the resistance value of one resistor plus 1 over the resistance value of the other resistor. When you multiply that out, you get 1.5 ohms. Okay, so the equivalent resistance is 1.5 ohms. At this point, what I encourage you to do, anytime you find an equivalent resistance, redraw your circuit. Now, it might seem a little silly to do that right now when there's only two resistors and you know that one resistance value is 1.5 ohms and it's kind of not a lot to write. But imagine when these resistors circuits get larger and a little bit more complicated. It's good to have that practice and know, okay, well, I can redraw the circuit. Now I can see that the current passes through that 1.5 ohm resistor, and I can use Ohm's law in order to find that current value. So I know that there's 3 volts. I'm trying to find my current, and I know my equivalent resistance is 1.5 ohms. So I can divide by 1.5 ohms, and I can get my current value. 3 volts divided by 1.5 ohms gives me 2, and the units of current are amps. So although I wasn't asked to find the equivalent resistance, I needed to find the equivalent resistance in order to apply Ohm's law to calculate the total the amount of current supplied by the power source. Now that's part A. Part B asks specifically for how much power is consumed by the resistors. Well, you know the power equation is power equals current times voltage. So now that I know the current that passes through both resistors is 1.5 ohms, I can utilize this equation. I can say 2 amps, because that's the current that leaves the power source and goes through the resistors when they're in equivalent resistance together. And I know that it's 3 volts. So I can say my power is 2 times 3, which is 6. And what are my units of power? Watts, 6 watts. An alternative way of solving that would be to look at the form of power equation. You could use the V squared over R. And in this case, what R would you use? Because it says by the resistors plural, you would need to use equivalent resistance. So you can say 3 volts squared over 1.5 ohms. And you should get 6 watts. Again, yes, 6 watts. So no matter the form of the power equation that you use, whether you use this form or this form, the P equals IV or the P equals V squared over R, you should get the same resulting value. So what if you're given a circuit that has both series and parallel components? You're not always given just a pretty series circuit or a pretty series parallel circuit. A lot of times you'll have multiple resistors within a circuit that have some in series and some in parallel, and then those might be in series with other parallel parts, and it can get a lot more complicated. You can utilize these techniques of combining series resistors or combining parallel resistors within the overall larger circuit. You can break them down into smaller pieces. So here's a procedure, an algorithm that you can implement in order to help you solve it. So we'll use this circuit right here as an example. And you can see that this resistor right here, this 50 ohm resistor, is in series with this 150 ohm resistor. You can tell that because if you were current passing through those, you wouldn't have to have multiple loops to go through each individual one. You can go through one and then pass right through the next one. Now when you get through here, you'd go this loop here like that, and then you could go this loop here through this 100 ohm resistor like that, and then combine back together. So you can see that there's 2 loops here. So you would want to maybe identify these 2 as parallel. And so that can help you when you're trying to combine those. So if you look, the easiest thing to do is combine series resistors. So that can be step one. Combine any obvious series resistors. So if you combine 50 and 100, so basically you would have, I'm going to call this segment A. And so I'm going to find REQ of A. And I'm going to say 50 ohms plus 100 plus 150 ohms is 200 ohms. Now, once you compute the series, or once you compute a equivalent resistance, you should always redraw your circuit, just so you can see what you're working with. It might give you some more insight on other parts of the circuit. So this is 5 volts, this is 200 ohms, this is 100 ohms, and this is also 100 ohms. And you can see, okay, well, I have these 200 ohm resistors, and they are in parallel with each other. We're going to call this whole segment here segment B. So I'm going to find REQ of B. So my algorithm is first bind series resistors, then redraw the circuit, then compute any parallel resistors. So these are in parallel, so I'm going to do 1 over 100 ohms plus 1 over 100 ohms. And when I combine those together, plug it into my calculator, I get 50 ohms. Take a second, make sure that makes sense. 50 ohms is less than the smallest resistor in the circuit. And I'm also noting that 50 is half of 100. So whenever these resistors that are in parallel, if they're the exact same value, the equivalent resistance is just half of them, which could be useful to help you solve these circuits a little bit faster. So now that I have REQB, I'm going to redraw my circuit again. And now notice how redrawing that circuit helps me realize that resistor 1, here, this 200 ohm REQA and REQB are in fact in series with each other. So now I can repeat my steps. I can see, are there any adjacent series resistors in series? The answer is yes. So now I can look at these and I can find the overall equivalent resistance, REQ, is 200 ohms plus 50 ohms, which is 250 ohms. So if I redrew my final version of my circuit, I have one equivalent resistor, plus minus 5 volts, and it's 250 ohms. And now if I were to need to find power or current passing through it or any other information, I can utilize that equivalent resistance. So don't be intimidated by a big, overwhelming circuit. Break it up into individual parts. Combine the series. Look and see if you can identify which resistors are easy and in series. Add those together. Redraw your circuit. See if you can find clear parallel components. Combine those into equivalent resistances, and then simplify the circuit, redraw it again, and you might be able to see, oh, these are now in series with one another, and just repeat the process over and over until you get it down to one individual resistor. Don't try and combine multiple things at one time. Take it slowly, one piece at a time, and you'll be able to find the equivalent resistance and then solve the problems accordingly.